Okay, so I will start now going through this mandatory assignment 1. And it was. I think that some of you might have been a bit confused as to how to do this. Uh, and I think there are two culprits. One is the slides that I think had some ambiguity to it and something that wasn't exactly how it should be. So I'm also trying to figure out where the slides is for the Elgamal. Does anyone know which set of slides that is? Probably secure challenge, key exchange probably. Let me just get this up, and let me get the chat up here. Okay. Elgamal. Let me just get it up so I can put it in here. So let's see what we have to do. Diffie Hellman, attack. Okay, so anyway, if no one can tell me where the Elgamal slides are, I will just I'll just go with the flow then. Okay, so we are Alice and we want to send 2,000 kroner to Bob through a confidential message, and we will use Elgamal public key method. The keying material you should use to send to Bob is as follows, and I will be using Python, so let's save this as Python. Okay, so the shared base G we set to 666, and no thank you. And the shared prime we set to 6661, and the Bob's PK. Let's set that to what it says here. PK Bob 2227. Right. And let me just get the chat up over here, and you can ask questions if you need to. Okay, so how do we do Elgamal? Okay. Oh, I need an equal sign here. Alice will choose a random integer within the ring. So let's make a part 1 here, and let's say that the message is 2000, and Alice will choose a random y, and let's just say 201. It's within the ring, which is 6661. Okay, then we will now get the PK Alice, public key of Alice, and we'll call it PK Alice, and we'll set it equal to pow g y p. And what this does in Python is that it will take g to the power of y, and then under modulo p. We could also write this as g dash like this in Python, y modulo p. But I think for very big numbers this doesn't work so well, because it will actually evaluate this whole term and then take it modulo. And if the numbers are huge, then it will halt. So this is some cool, fast way to do it in Python. Now we will need the gxy to be pow of pk Bob, the y that Alice chose, under modulo p. So now we have this secret key that we can send to Bob, or we can use to encrypt the cipher message, or the plain text, the message here, to get a cipher message that we want to send to Bob. So let's make that c equal to gxy times the message. And here is where a lot of you got this wrong. Not all of you, but many people, they got this part wrong. And I guess it's because that somewhere in the slides where Elgamal is shown, this is just what's shown. But when we are in Elgamal, or whenever we are talking like group theory and crypto therein, we always need to stay within the group. So we need to take this modulo p. Let's see if Elgamal slides were under lecture 4. Here, let me just get this up. Elgamal. Can someone say where in the slides the Elgamal is, because I want to show. Okay, this is I understand why many of you got this completely wrong because the slides are terrible. And I don't blame you so much. So let's look at what the slide says. So here we have Elgamal. We are Alice. We choose a random x. We call this y. Compute g to the power of y, and then we send this over. We already. Oh, this is Bob, and we've already done this step. And then we want to pick a y, take this, and this is what we've done here. And then we want to. It's not even set here, but this should have been mod p. And I don't blame you for not understanding this part. But it was discussed in the forum, but it should have been more specifically that this part needed to be mod p, because it always is. And if you looked up any other um, way, you would see that this is always mod p. Um, anyway, then we sent this part to Bob, g to the power of y mod p, and this ciphertext which has been multiplied with the gxy, and then or the receiver can then compute. Yeah, we'll get to why this part is not doesn't work either. But let's get to that in a second. But what is important that I think many people miss, that this needs to be under mod p. It can't exceed the group, and it never will. So I don't blame you for misunderstanding this, because there is definitely some ambiguity here. But I hope that I can clear this up. So let's move on. And I might pick up these slides again at some point. Thank you, Petja and Jonas, for pointing out where the slides were. Let's print out some. Now we have the C, and let's print. I actually already wrote this, so I'll just bring this in so I don't have to write it again. Sending g to the power of y, and we get it's the pk Alice. This is the g to the power of y, and C from Alice to Bob. And this is the first part, and we don't have to do any more here. Or maybe let's try to recover the message and decrypt it, and I'll show you why there was some why it needs to work in a different way. Bob recovers a message by calculating c g to the yx. We actually want c to be multiplied with t to the power of y x. And we need that to be the multiplicative inverse. This is how we write this. And I will get to what this is in a second. So we get the gxy minus 1, the multiplicative inverse, by saying, and this is the part I will explain in a bit. I'll just write it out first. Pow, and we need gxy minus 1 under p. And then the message reconstructed. I'll just go through this. This might not make a lot of sense to those of you who just divided in a second, but let me show you why. Modulo p, and print Bob recovers the secret. Print message reconstructed. Let's see if we can run this. Oh, am I not in the... Where did I put this? Home meal. Day. Home. Maybe I'll just run a terminal here. Oh, it's terribly... / home meal. Oh, like this. Yeah, it's better like this. Python 3 elgamal.py. Yes, sending g to the power of y. This is the g to the power of y, and this is the c. And Bob recovers the secret, as we see, 2000. Okay, so let's look at the slides real quick. and let me tell you why it doesn't make any sense, but I guess it's the notation that it should have been more talked about. So when we are in a group, we cannot always divide. And that's why this was also a bit hard to understand. Like, you wouldn't really know you made a mistake because it didn't pop up with some error. We cannot always divide, and let's see if we can get a case where we can't divide. Let's change this text here, the message, to be 2200. We will hit a case where we can't divide at some point. Run this again. Okay, let's try and nudge this up to 6. This number instead. Oh my! Oh, we are not dividing. That's why it works. So let's see. We cannot always divide. Let me just come back to that conclusion. We can't always divide because sometimes we will get some number that isn't divisible to an integer, and that doesn't work under a modulo. So let's talk a bit about that. We do like this. Oops. Don't want that. We have our message m, and it's equal to some text, or it's equal to 2000. That's what we start with. Then we get the gxy, the key that we need to encrypt with, and this is also some number. It doesn't really matter. And what the C is gxy times m modulo p. P equals some number. It's not super important. Now, when we the logical step when we have C is equal to gxy times m to recover m would be to just divide by gxy. But as I just mentioned before, this doesn't always work, and I think that it's actually it's a kind of a special case in this assignment where it actually would work. So what we need to do instead is multiply m or c with the multiplicative inverse of gxy. And what is that? So the multiplicative inverse, let's call it multiplicative inverse, let's just call it this, is equal to the number divided by it's the multiplicative inverse. Let me understand how to say this correctly. Is the number that we need to multiply gxy with under modulo p, where we get 1. So the number is times gxy modulo p is equal to 1. So this number here that we don't know needs to be the number that we multiply gxy with under modulo p so that we get 1. This can be any number, and there are different algorithms to devise this number, and that's what I did here in Python. I set power gxy to -1 under modulo p. This will give me the number that I need to multiply gxy with under modulo p to get 1. And I'll just say it again. We have a key gxy. We need to find the number that multiplies with this number under modulo p that gives 1. I'll show it again. This number here, I'm sorry I'm saying it many times, but I just want everyone to understand, is the number multiplied with gxy under modulo p that gives 1. It doesn't always exist. Then something has been fucked up in the encryption part. Anyway, this number we can get in this formula here. Sorry for saying it many times, but it's very important. And let's see why it works. Because when we now have a number applicative inverse times gxy times m, now you can see that this is equal to multiplicative inverse times c, right? So we have c here up here, which is gxy, and this is all under modulo p. We have c, which is gxy multiplied with m under modulo p, and we want to recover m, right? So let's multiply with the multiplicative inverse on each side. And then we get now that we know that the multiplicative inverse times gxy under, of course, under modulo p is equal to 1. So we can now substitute this instead. So we get 1 times the multiplicative, or 1 times m, and we can substitute anything on the right side. But this turns into be m is equal to c times the multiplicative inverse. Lorenzo, I'm sure that you would have some nice way of saying this. It came out a bit confusing to me. I hope that it makes sense. Can you please let me know if this is totally not making any sense? I will try to formulate it in a different way.
I think it makes pretty good sense, but could you write up maybe more like a formula for the multiplicative inverse, so it'd be easy for the dumb one of us to just type in easily?
So like an algorithm to devise the multiplicative inverse.
Yeah, kinda.
Okay, so those of you that I talked to about this, about finding the multiplicative inverse, it's a few weeks ago.
Yeah,
Oh yes, go ahead.
Yeah, I think the key idea here is that should be very clear that you can find the multiplicative inverse in an efficient way. So if you in this case, since the group is small, you can finding the inverse using brute force. But if you are in a big group, then you must necessarily use an algorithm that is efficient.
Yes, and one I never I always just look up a multiplicative inverse function and just copy it in. I know some of you did this for Java as well, and I think those are pretty well optimized. I'm not entirely sure how it works under the hood in Python, but one that I brought in, let me just show it like this, and I'll see if I can understand the code myself. So this is a way we define a function in Python, def mod inverse, and this is the number that we want the multiplicative inverse for, and this should say p. So let's just change it. No, not pkbub. So what is done here is that we make sure that we are not exceeding the group. So we take a modulo p in the beginning, and then we say from 1 up to p, if a times, we just basically brute force this. So this is a brute force. Lorenzo, do you know if there are more efficient ways than just trying all the numbers in the group?
Just a second, I can share with you.
Okay. I'm sure that if you look up efficient multiplicative inverse, then there will be some other nice and fast way of doing this. I think for the sake of not taking this for the longest time, let Lorenzo, can you just put it in the chat and then people can look it up, because I want to get through this.
Yeah, sure. I'm gonna share it.
Okay, so let's just, now we know the two culprits that was in the assignment that was a bit making. I didn't fail anyone on behalf of this. I think it's a totally legit mistake to make when we have these slides where it basically looks like we are dividing, but the division here should be understood more of as a multiplication with the multiplicative inverse of gxy. And I understand why this was a bit confusing, but now I hope you understand why that it needs to be done in a different way. So let's move on with the assignment. Let me just get my up here. And Bob has recovered the secret. Now, I think most of you got this next part, right? Let's copy this right here. Copy this. You are now even intercept Alice's encrypted message. Find Bob's private key and reconstruct Alice's message. So now let's just brute force this. let's just brute force the key for I in range 1, 2, 6, 6, 6, 2, because I think it's non-inclusive in Python. If pow G I P, and Bob has sent his private key, so we can just look for it. PK Bob. Then we set x to be equal to y, or to I, and we print, haha, I found Bob's private key. Oh, and this needs to be outside. And break out of the loop. And that's basically it. I don't know, this part is not necessary. I don't know why I did this in my own code. I have my own assignment. Oh, yeah, we need to save this variable, that's why. So now we have it. And let's say that Eve can now calculate g to the xy, since g to the y is given from Alice. And let's make a variable Eve gxy is equal to pow, not very good at typing, very sorry, Alice xp. And this is the x that we found, Bob's private key. And then let's just take Eve gxy, the modular inverse, is equal to pow Eve gxy, comma minus 0, comma p for the modular inverse, and let's print some stuff. I am Eve. I find Alice message to be, and let's put this here, C time, because we observe the C, let's put it like the C times Eve gxy minus 1, we multiply with our multiplicative inverse, and like so. So now we can oh, and of course this needs to be modulo p. So now we this is Eve finding the message. Let's see if we can, and this needs to be part 2. Let's run this. Yes, and Bob recovers the secret like this. This could probably be on one line. Let's make it a bit neater, like this. And let's get one more print here to format it a bit more nicely. Let's clear this. So let's run. It looks like that. Sending g to the power of y, blah blah blah. This is the first part. Bob recovers the secret, which is this. Haha, I found Bob's private key. It is 66. I am Eve. I find Alice's message, and it's the same as up here. Let's change this back to 2000, because that was what we were originally working with. Yes. Very nice. And that was basically just part 2. So let's make a print statement for a break, and copy this for part 1 or part 3. And now we are just Mallory. We can look here. Now we are Mallory and we intercept Alice's encrypted message. However, we run a constrained device and are unable to find Bob's private key. We can't brute force it, but and this, I guess, was a bit also ambiguous in regards to how to do it. So modify Alice's encrypted message so that when Bob decrypts it, he will get the message 6000. And this was basically just to show that we can say that C is equal to C times 3. And then when we decrypt it, let's make it gxy minus 1 again. Oh. I know this has already been done, but I want to do it again for the argument's sake, or for the example's sake. And then print Bob now, let's say the message has been tampered with. Bob doesn't know this. The message is now and it's the c times gxy minus 1 or minus 1 modulo p. I think we need to put this in like this. And let's see if we can run it and we get the right results. Yes, so the message has been tampered with. Bob doesn't know this, but we could multiply it just with 3 to get the 6,000 here. And I mean, this is a bit lazily implemented, but it really gets the job done. I would probably add a bit more comments and stuff to this, but it works well. Servan asks if this is the only accepted solution for part 2. No, I guess if you manage to do this in some other way, then it's also accepted. Did you do it for some other way?
Yeah. So in line 37,
Yeah.
I actually don't have that at all. I used for line 36, I instead used a minus x instead of x to calculate the multiplicative inverse. So in line 36, you generate the public key for Eve, but I
No,
only use.
I get the GXY because Alice has sent her public key, and I just need to multiply that with the hidden x from Bob. So this is basically the GXY.
Yeah, but so wait, I can just send my code instead.
Yeah,
because it
sure.
will work for me.
Can you just send it to me, and I so s so this is the
And
negative.
message code.
Oh, I guess this might also work, but I can't look through and understand right now why this would work. But the negative of Bob private key. I really don't understand why this works. But maybe if you have some resource where you got it from, then I will gladly take a look.
Okay.
Yes. But if it gets the job done, then sure, then it's super good, and it's totally fine. Okay, this was the assignment. And I hope I cleared up why some of the mistakes were made and why you need to do it in a different way. Are there any questions now? Okay. Thanks for tuning in. I will put this code on a GitHub and share it with you so that you can compare it to your own implementation. I will just go offline for Discord for a bit to just put the stuff up. And then I'm sure Lorenzo will be here for the next bit, and Bernardo, he has helping hours at 12 where he can help you with the second mandatory handin. Okay, thank you.